Hello, my name is John Adamski, and this is Math 1106, Business Precalculus. This is lesson 1 of 12, weekly lessons that are going to prepare you for the class you'll take in the spring, Math for Business Calculus. We're going to cover all of the algebra and precalculus topics that you'll need for success in that course, and we're going to do it in as short a period of time as we can. All right? Lesson number 1, here's what I'm going to talk about today, exponents and radicals. When you get to calculus, you'll see that a lot of what you do is manipulate exponents. You'll have expressions that have all kinds of exponents, many exponents, negative exponents, and fractional exponents. And so I've broken today's lesson up into these 3 topics. At the end of this, we should be comfortable with exponents. Let's get to it. Okay. So here are the first 5 properties of exponents. You've probably seen these before. I'm not going to talk about them much right now. What I'm going to do is I'm going to walk you through some problems and show how I use these properties to simplify these expressions that have exponents. Taking a look at example 1a, I've got a fraction. In the numerator, I've got 2x cubed, all being raised to the 4th power. Take a look at property number 4. When you have a product of terms being raised to a power, you're supposed to raise each of those factors inside to that power. It's kind of like a rule of distribution for an exponent. You have to raise this to the nth power, that to the nth power. So in this fraction, just looking at the numerator right now, I've got a 2 times x cubed to the 4th power. The 2 needs to get raised to the 4th power, and the x cubed also needs to get raised to the 4th power. The same thing has to happen in the denominator, and this time everything downstairs needs to get cubed. The 3 needs to get cubed, and the x squared needs to get cubed. The parentheses here are being inserted so that you don't have a 2 right up against a 3, making it look like 23. No, no, no. This is x squared times x squared times x squared, i.e. x squared cubed. And so now, 2 to the 4th, I know what that is. That's 16. And x cubed to the 4th power, now take a look at property number 3. This shows us that when you have nested exponents, something with an exponent and parentheses, and that thing is raised to an exponent, I multiply those exponents together. Okay? So this 3 times 4 gives me a 12. And down here we've got 3 cubed. That's 3 times 3 times 3, which is 27. X squared cubed. I multiply the 2 times the 3, and I get x to the 6th. Okay? I'm almost done, but I've got an x to the 12 over an x to the 6th. And property number 2 tells me when you have the same base in the numerator and denominator raised to these exponents, you can subtract them, the top exponent minus the bottom. So if I've got an x to the 12 over an x to the 6th, in the end, that's going to give me the 16 and 27 can stay put, but now I've got x to the 12 minus 6. That would be x to the 6th. Okay? That would be my simplified answer for this one. Taking a look down here, it's the same sort of idea, but now I've got 3 factors being grouped together, all being squared. So it's this times itself. We could just copy and paste, say it's this times itself. Of course, property number 4 comes into play here. I'm going to square the first term, square the second term, square the third term. And so what I've got here is 2/5 squared times x cubed squared times y squared. Okay? And when you come to this fraction with a power, with an exponent here, I look down at property number 5, which tells me that I need to raise both the numerator and the denominator to that power. So it's, again, a bit of a distributive property for an exponent acting on a fraction. So what I'm going to do is I'm going to square the 2. That's going to give me 2 squared, which is 4, over 5 squared. Okay? Over here we've got, well, I might as well just write that. I've got 4 over 25. X cubed squared, we've actually seen that one before. We know that that's x to the 6th. We know to multiply nested exponents. And I've got a y squared at the end. Now you certainly could leave your answer like this. This answer is simplified. Another thing you could do is consider, okay, this x to the 6th is an x to the 6th over 1. This y squared is a y squared over 1. And when I multiply fractions, I multiply the tops together. I multiply the numerators. So in the end, this is a single fraction where the numerator is 4 x to the 6th y squared, and the denominator is 25 times 1 times 1, so just 25. Okay? Again, the answer I had before, nothing was wrong with it. It was totally simplified. Just want to show this can be written as one fraction, which is sometimes preferable. All right, let's take a look at example 1c. This one's got a lot going on here. Let's see, we've got 5 to the 4th upstairs, a 5 squared downstairs. This property, number 2, tells me that when you have the same base upstairs and downstairs with these exponents, you subtract exponents, the top one minus the bottom one. So if I go along, working my way from the inside out, starting inside the parentheses, we'll handle this squaring at the very end. I've got 5 to the 4th over 5 squared. That's a 5 to the 4 minus 2, leaving me a 5 squared. I've got x to the 4th over x. That's an x to the 4 minus 1. There's a hidden exponent of 1 here. Okay? 4 minus 1 gives me 3. Then I've got this term, x squared plus 1. There's an x squared plus 1 both in the top and in the bottom. That's the same base in the top and the bottom. I subtract the exponents. 3 minus 2 gives me a 1. I don't have to write the 1. It's implied. And that still needs to be squared. Well, I look at property number 4, which tells me that every term inside the parentheses needs to be squared. So we've got 5 squared squared, x cubed squared, and x squared plus 1 squared. That's 5 squared squared times x cubed squared times x squared plus 1 squared. In the end, this is a large number. I'm just going to leave it as 5 to the 4th power. 2 times 2 is 4. 5 to the 4th. That would be 625. X to the 6th, x squared plus 1 squared. And that's my final answer. Okay, now let's talk about negative exponents, and an exponent of 0 for that matter. I've got a little table here, and I've filled out part of it. In the top row I've got values for n. In the bottom row I've got values for 2 to the n. So 2 to the 1st power is 2. 2 to the 2nd power is 4. And 2 to the 3rd power is 8. We know that. And as you move to the right, you see that we're just doubling because we're adding an extra factor of 2 every time. Times 2 as you go to the right. Well, the pattern can be extended to the left as well. If I go from 8 to 4 to 2, I'm just dividing by 2 each time. So 8, 4, 2, the next number should be 1, and the next number after that should be 1/2, and after that should be 1/4, and after that should be 1/8. Just extending the pattern to the left. And that is exactly what we mean by 2 to the 0th power is 1, 2 to the -1 power is 1/2, etc. This is how we define negative exponents. In summary, if you want to raise something to the -nth power, you're going to raise that thing to the nth power and then just take its reciprocal. So you'll see that, for example, 2 to the 1st and 2 to the -1st power are reciprocals of one another. The fraction has been flipped. The same is true for 2 to the 2nd and 2 to the -2nd power. Those are reciprocals. Okay? And in the middle, you have a number whose reciprocal is itself. The only number whose reciprocal is itself is 1, well, and -1, but in this case, 1. Any number raised to the 0th power would be 1. Okay? And so similarly here, what does it mean to take the reciprocal of x to the -nth power? Well, we know that this is the reciprocal of x to the nth. This is the reciprocal of the reciprocal of x to the nth. So that gets you right back to x to the nth power. Let's look at an example. Just evaluating 2 to the -3rd power. This is just a, do you understand the definition of a negative exponent? I hope so. That's 1 over 2 cubed. That's 1/8. And that's it. Now we've got something a little more complicated. I've got a fraction in here all being raised to the -2nd power. Okay? I still have to apply the exponent properties that I reviewed previously. Those still play a role. So if we start inside the parentheses, let's see what can be said. The first thing I'd like to do is just point out that this 1/3 can be written with an exponent. That's the reciprocal of 3. So it could be written as 3 to the -1, right? Okay. And so what these properties are telling us is that when a term has a negative exponent, it should really go to the other side of the fraction with a positive exponent. Something that's in the numerator with a negative exponent should go to the bottom with a positive exponent. Something that's in the bottom should go to the top with a positive exponent. So I'm going to really put these things where they belong, what's inside the parentheses right now. All right, so that 4 can stay. This x to the negative 2 can come downstairs. Maybe I should start with the numbers. This 4 can stay. This 3 to the negative 1, let's bring that upstairs with a positive 1 exponent, okay? This x to the negative 2 upstairs should become an x to the positive 2 downstairs. This x to the 4th can stay. It has a positive exponent. This y to the 5th can stay upstairs. But this y to the negative 3rd, because that exponent's negative, it should really go upstairs with a positive exponent. Okay? Now let's just clean up what's inside the parentheses before we handle this negative 2. 4 times 3, of course, is 12. Y to the 5th times y cubed. The property for exponents that I'm using here is that I add the exponents when I have two terms with the same base being multiplied together. I add the exponents. That's a y to the 8th power. And in the bottom, I have an x to the 6th power. Again, I add the exponents. And this is being raised to the negative 2. Now, you're welcome to break this up into 2 steps if you want to. I'm going to square this, and then I'm going to raise it to the negative 1 power. Now, with nested exponents like this, the property for exponents having to do with nested exponents says that they should multiply together, and these multiply together to be negative 2. So these are the same expressions, but this is just going to break this up and maybe make this a little bit easier. It's easy to square. It's also easy to take the reciprocal. To raise something to the negative 1 power means to take its reciprocal. So I'm going to square everything inside here. I'm going to square the 12, the y to the 8th, the x to the 6th. That's going to give me 144. Y to the 16th power divided by x to the 12th power. And when I take the reciprocal of that, I'm just going to flip the fraction is all I have to do. So my numerator will be x to the 12th, and my denominator will be 144 y to the 16th power. And that will be my final answer. Okay? All right, let's try and simplify this expression. Just as before, I see that this has a 1/2 in here, and that 1/2 can be written with a negative exponent. That's a 2 to the negative 1st power. So the first thing maybe I'll do is I'll replace that 1/2 with a 2 to the negative 1. Okay? And that immediately tells me that that 2 should really go downstairs, right? So if I'm trying to simplify this, maybe the first thing I'll do is bring that 2 downstairs. So there is a 2 and a 14 downstairs. Now I've got a single x upstairs and 2 x's downstairs. There's a cancellation that can be made. I have 1 extra x downstairs. If you're using the property of exponents, you'd say that x divided by x squared would be x to the 1 minus 2. There's an exponent of 1 there, 1 minus 2. That would be x to the negative 1, which would be an x to the positive 1 power in the denominator. And lastly, I've got x minus 4 to the cubed over x minus 4 to the 1st. I subtract the exponents. 3 minus 1 leaves me with a 2. X minus 4 squared is my numerator. I still have to raise this to the power negative 1. That just means to take the reciprocal. So my denominator of 28x becomes my numerator. And my numerator of x minus 4 squared becomes my denominator. And that's it. Let's look at a simpler example and just touch on one very important thing about exponents. It's important that we understand the difference between this expression here, 2x to the negative 3rd, and this expression here, 2x to the negative 3rd. It sounds the same, but you can see that they've been written differently. So what is the difference? Well, the difference is what the exponent is acting on. Here, as you see, exponents only act on what they touch. So that negative 3 exponent is only touching the x. So the x is being raised to the negative 3rd power. The 2 is not. So this thing on the left is a 2 times x to the negative 3rd, which is a 1 over x to the positive 3rd. Okay? And if you want to write that as a single fraction, you certainly can. That's 2 over x cubed. That's this expression. Now over here, now the negative 3 exponent is touching the 2 because the 2 has been grouped together with the x. So now both 2 and the x are being raised to the negative third. And if you want, maybe you want to write this as 2x cubed to the negative 1, just to break up the handling of that negative exponent to make it as simple as possible. Now, from the properties of exponents from earlier, we know that I have to cube the 2, that gives me an 8, and I have to cube the x, that gives me an x cubed. And that needs to get raised to the negative 1. Now, what does it mean to raise something to the negative 1 power? X to the negative 1 would be 1 over x to the 1. That means that x to the negative 1 is 1 over x. It means to take the reciprocal. So we're just going to flip this fraction. It doesn't look like a fraction, but everything can be written as a fraction over 1. So its reciprocal is simply 1 over 8x cubed. And that's my final answer. Okay? Notice that here the 2 was not cubed and it was not sent to the denominator because it didn't have an exponent attached to it. Here the 2 was cubed and it was sent to the denominator because it did have an exponent attached to it. Okay, and lastly, let's take a look at what happens when our exponents are fractions. Starting with very simple fractions called unit fractions. If I have x to the fraction 1 over n, where the numerator of that fraction is 1, x to the 1 over n. Turns out that that's the nth root of x. Okay? What do I mean by the nth root? Well, 64 to the 1/3, if we're following this rule, 64 to the 1/3 power would be the cubed root of 64. That's how you would read this. And the cubed root of 64 is 4. That's because 4 cubed is 64. That's what the cubed root is. The cubed root of 64 is 4 because 4 cubed is 64. Okay? Now, why do we have an exponent of 1 over n taking the place of the nth root of x? Why is that what this is? Why is x to the 1 over n equal to the nth root of x? Well, whatever x to the 1 over n is, it should be, if I were to raise it to the nth power, knowing the properties of exponents, that these nested exponents multiply, if you multiply those exponents together, you get 1. So x to the 1 over n is some number that when I raise it to the nth power, I get x. That is the nth root of x. Okay? So that's why this is what it is. As a special case, if you're raising something to the 1/2 power, that's the square root, and we don't write the 2 there. You could, but that by default, without any number there, it is the square root. If you want the cubed root, you need a 3. The 4th root, you need a 4, etc. Okay? And how does that help you handle x raised to any fraction at all, a over b? Well, you simply break it up according to the properties of exponents that we know. You could write this as x to the 1 over b raised to the 8th power. Multiplying those nested exponents gives me a over b, but now I have an intuitive way of understanding what this means to do. Take the bth root of x and then raise that to the 8th power. Okay, that could also be written like this. You could switch the order here. You could first raise x to the 8th power and then take the bth root of that, but this is not really advisable, and rarely is this better, because when you raise x to the 8th power, that generally means that you're going to be now working with bigger numbers, and now you have to take the bth root of an even bigger number than what you started with, and that usually makes the problem a little bit harder. Okay? So I generally won't do it this way. I'll take the root first and the power second. Let's look at some examples. The directions say to simplify. What I'm going to do in these first two is just evaluate this. This is a number. What number is it? Well, we'll follow this property of exponents to say, all right, well, this is 4 to the 1/2 power to the 5th power. I'm breaking that fraction up. 4 to the 1/2, that means take the square root of 4. So that's 2. That's 2 to the 5th power. 2 times 2 times 2 times 2. That's 32. Okay? It's the same idea here. 27th to the 2/3 power. I'm going to take 27 and take the 3rd root, or the cubed root of that, and then square it. The cubed root of 27 is 3, because 3 cubed is 27, and when you square that, you get 9. Okay? Now I've got a complicated expression here, or so it seems. It will actually be easy to handle if we switch notation. Instead of using these radical symbols, that's the name for this funny shaped symbol, that's a radical symbol. Instead of using that symbol to express this quantity, let's use exponents. The reason being, we have all these properties of exponents that make life easier. So how would you write this? Working our way from the inside out using exponents. I'd write x times x to the 1/2, and then I want to take the cubed root of that, so I want to raise that to the 1/3 power. Okay? Now you could distribute this exponent of 1/3, but let me work my way from the inside out and realize that this is x to the 1st power times x to the 1/2 power. If I add those exponents together, 1 plus 1/2 is 1/2, which is 3/2 as a fraction. And with these nested exponents, I now multiply them. The 3's cancel. I'm left with just x to the 1/2 power. Okay? If you want, you could write it as the square root of x. But you know, in a calculus course, exponents will be preferable over radicals simply because they are much easier to work with. So, I mean, both of these answers are correct. I'll leave it as x to the 1/2 power. And now let's look at this last example. This x times radical x in the denominator, we already know that that's x to the 3/2. We just did that. So this is what we're looking at. We're looking at 125 over x to the 3/2, and all of that is supposed to be raised to the 1/3 power, or negative 1/3 power, rather. So why don't I split that up into 2 steps. First, I'll take the cubed root of this fraction, and then I'll take its reciprocal. Those nested exponents multiply to be negative 1/3. This just makes it easier for me to wrap my head around what needs to be done. Okay? So to show all of my work here, I'm going to raise 125 to the 1/3 power, and I'm going to raise x to the 3/2 in the denominator, also to the 1/3 power, and the last thing I'm going to do is flip that fraction. So the cubed root of 125 would be a number that when you cube it gives you 125. The answer is 5. 5 cubed is 125. And downstairs I have a property of exponents that says to multiply these, which ends up giving me x to the 1/2. Okay? There's still this exponent of negative 1 on the outside, which means to flip the fraction. Okay? So I'm going to write x to the 1/2 on top and 5 on the bottom, and I'm just going to leave my answer like that. Okay, here's one more example. These are some common expressions that you'll see in a calculus course. They're going to pop up quite often, especially this first one. And so just so that you're prepared when you see it, let's just go over it. It's not a very big deal. Let's just think carefully through what's going on here. I want you to just verify that what's on the left is the same as what's on the right. That's the idea here. Okay? And maybe you can kind of see that they're simply just using different notations. One is making a coefficient of a variable raised to an exponent, whereas another one is a single fraction where we're using radical notation instead of exponents. But they are the same thing. To see why, let's just unpack this, okay? So we know that this is 1/2. I'm just starting with what's on the left, and I'm going to turn it into what's on the right. I've got 1/2 times x to the negative 1/2 is a 1 over x to the positive 1/2, correct? And the way that fractions multiply, we multiply the tops together, so 1 times 1 gives me 1. And I multiply the bottoms together, that's a 2 times the square root of x. That's what x to the 1/2 power is, right? So that's a 2 square root of x. And so I see, yes, those expressions are the same. What's going on over here? Well, maybe we can figure this out or verify that the left is the same as the right using exponents. So let's switch notations. Let's write this as x plus 5 divided by x plus 5 to the 1/2 power. Now, the numerator is x plus 5. You can think of that as x plus 5 to the 1st power. Nothing wrong with that. So there's a base of x plus 5 upstairs and downstairs. The rule of exponents says to subtract the exponents. 1 minus 1/2. This is going to give me x plus 5 to the 1 minus 1/2. That is x plus 5 to the 1/2 power, which can also be written as the square root of x plus 5. So these expressions are in fact the same. Okay? There's another way to do that that's a little bit cute. You can say, well, the square root of x plus 5, this expression that I'm starting with, that numerator is the same as the square root of x plus 5 times the square root of x plus 5. divided by the square root of x plus 5. So I'm replacing x plus 5 with its square root times itself. That'd be like replacing 9 with 3 times 3, or 16 with 4 times 4. This is fine, and now you can verify it another way by simply canceling the common factors upstairs and downstairs. But the rules of exponents handle this just fine. In example C, it looks very similar to example B, except you'll notice that 5x minus 9 and 9 minus 5x are not the same thing. So if I try to write this as, let's see, I didn't say what this is supposed to equal, but we'll just go with it. I want to verify that this is equal to negative square root of 5x minus 9. That's what I want to do. Anyway, so like I was saying, the 5x minus 9 and the 9 minus 5x are not the same. Those bases are not the same. But notice that 9 minus 5x is the same as negative 5x minus 9 divided by the numerator, which I'm not going to change. I'm just going to rewrite using exponent notation. So just to follow along with what I just did, if you distribute this negative sign, there is a negative 5x, just as there was before, and there is a negative 9, or in other words, a positive 9. So after distributing that negative sign, you do have exactly what is upstairs. These are the exact same thing. But now you can proceed just as in example B, and you can say that this is negative, because that negative 1 isn't going to disappear, negative 5x minus 9 to the 1 minus 1/2, which is 1/2, okay? And that, of course, is the same as negative square root of 5x minus 9. So that verifies it. So there was a property of real numbers that we used in the last example that's important to make note of, because it pops up from time to time and is useful. If you ever have a difference, a minus b, and you'd prefer to have a b minus a, you prefer to switch the order of subtraction, you can do that. But know that when you do switch the order of subtraction, you're going to negate the answer. So to compensate, you have to negate it, okay? So that when you switch the order of subtraction, as long as you insert you multiply by negative 1, things are unchanged. You still have a negative b, you still have a positive a, okay? Let's just do one last example, then we'll be done. I want to verify that this expression here on the left is the same as this expression here on the right. And as has been sort of the theme, it's easier to work with exponents than it is to work with radical signs. So the first thing I'd like to do is just switch to exponent notation. So let's write this as x to the 1/2 power. And when I come to 3 minus 7x, looking downstairs that there's a 7x minus 3, these are going to be able to interact if I rewrite this 3 minus 7x as a negative 7x minus 3. Okay, so that negative sign is here, and I switched the order of the subtraction. So those two switches cancel each other out, and this is the same expression as what's above. Downstairs we have x times 7x minus 3 to the 1/2 power. Okay? So using some rules of exponents, what am I left with? Well, negative 1 times x to the 1/2 minus 1, that would be negative 1/2, times 7x minus 3 to the 1 minus 1/2, that would be 1/2. Okay? So what we have here is negative. If I write this as a fraction, we have 7x minus 3 to the 1/2 power divided by x to the 1/2 power. I'm sending that x with a negative exponent downstairs with a positive exponent. Okay? Now I could just stop here, but I'm trying to verify that what I started with is equal to this, and I haven't yet arrived at this. So what is left to do? Well, perhaps you want to realize that both the top and the bottom are being raised to the same exponent, 1/2. So this could be written as 7x minus 3 over x to the 1/2 power. More efficient this way. Just write 1/2 power once, and it applies to both the top and the bottom of the fraction. And now, to get to the end, I'm simply going to replace the exponent notation of raising this to the 1/2 power and replacing that with the radical notation, taking the square root. It means the exact same thing. So in the end, these are exactly the same expression. And that's it. You'll find in Blackboard a list of, I believe, 11 practice problems similar to these. Solutions are posted. Test yourself with those. Work through those 11 problems. It shouldn't take you that long. Please don't rush. Take your time. And when we meet in class, we can go over those. If you have any questions, you can ask. And then you'll complete a worksheet on some similar problems. Okay? All right. Thank you.